Random response linear dynamic analysis is used to predict the response of a structure subjected to a continuous excitation. Here, after running a modal frequency analysis, we're going to focus on one part of the satellite assembly to run the random response analysis. Choosing a new analysis, we can select random response. As this part will be a laminate component, we will define two materials. One, a 2D orthotropic carbon epoxy, and the other, a standard isotropic material. You can see the various layers of the laminate defined in this table. Defining an element size of 2 will provide us with a consistent mesh across the part. Oftentimes, in a random response analysis, your loads will be represented by concentrated masses. These are applied via connectors, in this case rigid bodies connecting the edges of the panel to a common center point. The process will be repeated for another group of rigid elements. Selecting the first connection point of the rigid elements, we can define a concentrated mass, representing a large unmodeled component. This can again be repeated for the other connectors. A boundary condition restricting the rotational degrees of freedom will be applied to the connectors, as well as a load of 1 e to the 7 pounds force. The load scale factor versus frequency table must also be defined. We must also set frequency range and spread around modes. This will define the range of excitation of the design. This data will normally have already been gathered for you by physical testing or previously run analyses. Showing the XY plot will display your inputs to help you verify accuracy. Defining the modal setup will allow us to determine how many modes we will solve for, as well as the minimum and maximum range. With damping defined, we will now be ready to run the analysis. As shown here, you can view the von Mises stress of any of the layers of your laminate to ensure that your setup will withstand the excitation of your random response analysis.